Have you ever heard of something that gets stronger the more you pull on it? It sounds, it sounds impossible, right? Like it breaks the laws of physics. But that's exactly what we're going to dive into today. A wild type of steel that completely rewrites the rules of engineering.
In the world of materials, there's always been this fundamental trade-off. If you make something stronger, it almost always gets less flexible. It gets brittle, it's more likely to just snap. And on the flip side, if you want something to be more flexible so it can stretch and bend without breaking, it's usually a lot weaker. You pretty much have to pick one or the other.
But here's the thing, modern industry just can't settle for that trade-off anymore. Take the car industry, for example. You need your car to be incredibly strong to keep you safe in a crash, right? But you also need it to be lightweight for better fuel efficiency. And that means the steel has to be formable, that it can be stamped into really complex shapes, like a car door, without crocking under all that pressure. So this brings us to the big question, the mystery we're going to solve. And this isn't just some random what if. It's the absolute key to understanding this amazing class of materials called trip steels and how they they throw out the old rule book. All right, so first, let's just take a look at how different these steels really are. The numbers here are, frankly, pretty mind-blowing. And wow, this chart really shows you what I'm talking about. See the bar for conventional high-strength steel? It's got okay strength, but it really doesn't stretch much. Now, look at the trip steel. It's not just a little stronger. It's almost 3 times stronger than the steel they used 30 years ago. But the craziest part is its elongation. It has insane strength and incredible flexibility. It's the best of both worlds. Okay, so how on earth is that possible? How does it just ignore such a basic rule of material science? Well, the secret isn't something you can see. It's something pretty amazing happening down at the microscopic level. The name, TRIP, actually gives us a big clue. It stands for Transformation-Induced Plasticity. Plasticity is just the sciencey way of saying it can be bent or stretched into a new shape permanently. So it's all about the shape-shifting trick the steel does, where its internal crystal structure literally changes its form on the spot. It's called a martensitic transformation. So picture the steel's internal structure when it's just sitting there. At a microscopic level, it's this neat, orderly grid of atoms. And this calm, stable state has a name, austenite. But here's where the magic happens. The second you start to pull on that steel, the stress acts like a trigger. And instantly, some of those calm austenite crystals just morph. They shear and transform into a brand new structure that's way harder and stronger. And that new structure is called martensite. And this is where the steel gets incredibly smart. It is actively, intelligently adapting to the force you're putting on it. This isn't some random change. The stress only triggers the transformations that are perfectly aligned to fight back against that specific pull, basically building a custom reinforced internal skeleton on the fly. Now you're probably thinking, okay, that shape-shifting trick explains everything. But there's a plot twist. That transformation, it's not the whole story. Not even close. See, here's the thing. In a typical piece of trip steel, only about 14% of the material is actually that shape-shifting austenite. The rest of it is made up of other, more normal forms of steel. So if you do the math, the actual amount of stretch you'd get from just that little 14% changing shake is only about 2%. A tiny amount, which is nowhere near what we see in the real world. Because when you actually test a piece of this steel in a lab, the total amount it stretches before it finally breaks is a whopping 25%. So that leads us to the real puzzle here. If the transformation itself only gives us about 2% of stretch, where in the world is the other 23% coming from? Okay, so here is the real magic. It's not the stretch from the transformation, it's the hardening that it provides. Think about it. As you pull on the steel, a weak spot starts to form, right? But the stress building up in that one tiny spot instantly triggers the austenite there to transform into super hard martensite. And just like that, the weak spot becomes a strong spot. This forces the stretching to move to another, softer area, and then the same thing happens there. And this process just keeps repeating, spreading the strain evenly across the entire piece of steel, which lets the whole thing stretch uniformly without breaking. Now, this microscopic trick is absolutely brilliant, but it's only half of this innovation story. Because as amazing as those original trip steels were, they had a pretty major flaw that made them a real headache to actually use. So the first generation of these steels had a lot of silicon in their recipe. And the silicon was critical for getting that trip effect to work. But it had this nasty side effect. During manufacturing, it would form this stubborn, glassy oxide layer on the surface that was a nightmare to remove. It made the steel hard to paint, and worse, it made it prone to rust. So, to solve this problem, scientists tried something completely new. Instead of spending years and years mixing up different recipes in the lab, they turned to artificial intelligence. They used something called a neural network, fed it massive amounts of data on steel properties, and basically asked it to design a brand new steel from scratch. And you know what? It worked. The AI analyzed all these incredibly complex patterns and came up with a totally new formula. It recommended swapping out that problematic silicon for high amounts of aluminum and tweaking the carbon levels. The result was a completely new material called Delta TRIP steel. And this new AI-designed steel was a huge success. I mean, it completely solved the rust and manufacturing problems. Plus, it had incredible properties. It was super strong, it had that great elongation, and get this, it was easily weldable, which is really surprising for steel with that much carbon. It's a true next-generation material that outperforms a lot of the commercial steels used in cars today. So this whole story, it's about way more than just one cool type of steel. It really points to a massive shift in how we create the very stuff that builds our world. It all comes back to this one simple, powerful idea. If you can engineer a clever, microscopic mechanism, this work-hardening capacity, you can design a material that gets stronger exactly where and when you need it to. And that lets you achieve that combo of strength and flexibility that we once thought was totally impossible. And that leaves us with a really fascinating thought. We're moving into an era where we don't just discover new materials through trial and error anymore. We can now use incredible tools like AI to design them from the ground up, basically programming them to have properties that used to be pure science fiction. So the real question is, what are we going to design next?